Okay, Ron, take it away.
So this presentation, what we're looking at is talking about how the advent of microprocessor technology being married to liquid analytical devices and how this marriage of these two technologies is allowing the industry to become much more efficient versus the older technology. And when you're looking at liquid analytics, it's very common that you see these in a variety of industries. There really isn't an industry that you wouldn't find liquid analytics, whether that be pH, ORP, conductivity, or dissolved oxygen. And they're used in a variety of different ways, whether it be in the process side of an industry and or also in the lab. So it's very common to find them in both sides of your business. And additionally, these measurements over the past decades have been used for both process control as well as monitoring. But with that said, there has been a significant cost to the end user to maintain these technologies. And there's a number of reasons why that is, and we're going to talk a little bit about some of the limitations of what is considered the current technology as it stands today. And we typically refer to that current technology as analog technology. And we're not talking about the output from the transmitter, but the signal between the electrode and the transmitter itself. Today, a lot of the challenges that you see in this technology has to do with the cable that's used to get the signal from the electrode to the transmitter itself. It's a coax cable. It's susceptible to noise, so there's some influences that can affect the signal quality. The next thing that you will typically see in this technology is the use of metal connections. A lot of times customers want the ability to do a quick disconnect, and in the image that you see on the slide, this is a variopin connection. The electrode itself has metal contacts that have to engage into that connector. So now if you're in an industry where there's a high moisture or an application with high moisture or corrosion, that will directly influence the quality of the signal itself. Cable length can be a limitation as well. A lot of times you'll see many applications where you have to limit yourself to under 40 feet. Otherwise, you have to use special signal conditioning to make sure that the quality of the signal being transmitted is good enough where you're not seeing influences from noise, but you're actually seeing the true process changes. Also, I already mentioned humidity and corrosion. Those are probably the two biggest things. So what you'll see is a lot of manufacturers will actually pot the cable directly into the electrode to eliminate that quick disconnect capability because they are battling that corrosion. So by potting the cable, you eliminate that, but at the same time, what you've done is you've moved the maintenance back to the transmitter, because every time you do a PM, you have to open the transmitter. But the final and probably one of the biggest challenges with today's technology is when you want to do PMs and calibration, you have to do those calibrations and that maintenance in the field. You have to take your buffer solutions, your cleaning solutions, things of that nature out to the process unit, because analog technology, when you do those calibrations, you have to calibrate the sensor, the cable, and the transmitter as one complete system. Otherwise, the system will not work correctly. So it forces you to be in the field to do those PMs. Now, let's talk about the microprocessor-based concept. So with the introduction of microprocessors, the biggest benefit is now what we've done is we've taken the processing or that calibration and we have moved it directly to the electrode. So what I'm able to do with a microprocessor-based electrode is that I can now bring that back to the lab and do those, or to the analyzer shop and do that calibration, because as you can see from the diagram, you've got your transmitter, field unit, if you will, and then you've got a cable where embedded in the cable in this connection here, and Eric, I don't know if you can see my cursor here, so just to make you aware, okay. You have a microprocessor embedded in this connector at the end of the cable, and then on the other side of that where the electrode is, there's another microprocessor. So what we've done in this case by introducing microprocessors into this technology is that it allows us a lot more freedom, and it gives us some advantages that you couldn't realize before. And primarily, one of those big advantages is an inductive connection versus a metallic connection that you saw on the previous screen. So now I have two coils, one embedded in the cable, one embedded in the electrode, and now when I have information, the pH value in this case and temperature, is being transmitted digitally across that inductive connection into a 4-wire shielded cable, which now we have really no practical limit on the length. So RS485 is the data communication taking place, and that cable can be, and again, this is the limit of 485, you could be up to 2,000 feet, but realistically, there's no practical limit, no amplifiers needed, and that's one of the a key benefit that you realize from this introduction of microprocessors into this technology. And back to the inductive connection for a moment, one of the real big advantages, game-changing advantages, quite frankly, is the fact that moisture is no longer a problem or something that's going to cause you to see a failure of the electrode itself. These inductive connectors are immune to moisture. We like to use the example of an electric toothbrush. You plug it onto the top of the stand, it's immune to moisture, it charges the electrode or the toothbrush. In this case, the same concept applies here. Now, moving on to some of the expanded capabilities with microprocessor-based electrodes is now we have the ability to truly have what we call predictive maintenance, because now with that microprocessor, we can constantly track time. We can use calculations to predict the number of days of life remaining in the electrode. We can transmit diagnostics information where previously you were very limited on what you could draw out of the electrode. Now we have the capability of truly pulling diagnostics information, which can then be shared with external systems, and then decisions can be made about what needs to be done with those measurements in the field, quite frankly, before a failure is actually realized, where it is starting to sense that there's a problem with the loop. You're not in a failure at that point, but it is giving you an advance notice that there may need maintenance done to make sure that you don't see the actual failure when it happens. Also, I mentioned before, because of the microprocessor that's in the electrode, I no longer have to calibrate the electrode with the transmitter and cable it's going to be used with. I can actually pull that maintenance from the field into a controlled environment, do my calculation, or I'm sorry, my calibrations in a controlled environment where temperature is no longer an issue. I'm not exposed to the elements, rain, snow, whatever it might be. I do my calibration with a portable calibrator. I disconnect the electrode from that portable calibrator, and now instead of taking all of my buffers and cleaning solutions, all I need to do is carry that pre-calibrated electrode out to the field, disconnect the sensor that requires maintenance, connect the new sensor, and it automatically uploads the calibration into the transmitter. So this is one of the biggest benefits to smart digital and microprocessor-based technology, in the sense that the time that was being spent in the industry to do PMs, because you were forced to be in the process unit to do them, is significantly reduced. So it frees up people who would normally be spending time driving around the facility, around the plant, doing these calibrations. That can be done at a more convenient time, and it can be done in a way that allows you to maximize the time spent in the plant doing other more critical tasks than trying to maintain the calibration on these liquid analytical devices. And one final piece of information to share, because we do have the ability to collect data, now there's the ability, especially if you're in situations where you have to record calibrations, document that the preventative maintenance is being done, because it's a Title V water permit where you have to show someone in the future that you are maintaining the measurements, you are doing the calibrations, there are software database packages that we can then bring to bear that stores that information. It's a non-alterable record of the calibration, which can then be later accessed and printed out to show that the maintenance is being done per the permit. So this streamlines the data collection perspective. It makes it takes a little bit more of that workload and moves it to the computer versus someone having to maintain paper records in those applications. So in conclusion, when you're looking at the microprocessor and how it's changed and brought on the smart digital technology, the values that you get from it, number one is significant time savings for PMs. You now can truly do offline calibrations at a more convenient time versus having to be in the process units. Reduction of the process data loss due to, for instance, when you're doing a calibration in the process unit, your measurement is down for the time you're doing that calibration. If that calibration takes 45 minutes, that's how much data you've lost during that period of time. Now, because of the quick disconnect and hot swapping, you're down 4 minutes. So your process data, the time that you're losing that data is very short now. As I mentioned, predictive maintenance. So in this case, because of the smart digital diagnostics, you have the ability to know in advance when there's going to be a problem with that loop because it's sharing that diagnostics data continuously, so you can then take actions before you actually lose the process measurement itself. And to sum it up, you have asset management software that gives you the ability to understand what's going on with each individual electrode, but at the same time, in situations where you need to store a record of the calibration, you now have that as a possibility as well, which could be shared with governing bodies, local EPA, whomever it might be. So with that said, I want to thank everyone for the time spent listening to the presentation and any questions. So what do you think, Eric?
It's fantastic, Ron. Really, really appreciate it. It was a great run through and really just a perfect summary of of how M4 Knick combined with Memosens is really making an impact in this industry. And gosh, we're seeing it every day. That's really exciting.